Hi everyone. Today's agenda for this video solution is to find the solutions of questions given in GET Chemical Engineering 2016 paper from mass transfer part. So here the first question is: a binary liquid mixture of benzene and toluene contains 20% mole percent of benzene at 350 Kelvin. The vapor pressure of pure benzene and pure toluene are given 92 kilopascal and 35 kilopascal. The mixture of follows Raoult's law equilibrium phase molar fraction of benzene in contact with liquid mixture at 350 is to be calculated. So here first we will denote x, we denote y b as the mole fraction of benzene in vapor, and yt as the mole fraction of toluene in vapor. Similarly, xb and xt. So here the 20 mole percent of benzene is given, that is in benzene is given as 20% of mole in liquid phase, so it is xb, that is given 0.2, and total that is pb, that is the vapor pressure of b, is given as 92 kilopascal, and toluene, that is pt, to we are denoting as given as 35 kilopascal. So these are the data that are given, and we are supposed to calculate this equilibrium mole fraction of benzene, that is yb. So we will apply the Raoult's law at equilibrium. The ideal at equilibrium, the Raoult's law ideal for Raoult's law for ideal solution is given as y, that is the fraction yb P total equals to xb into vapor pressure of B, that is if we are writing it for benzene. Similarly for toluene it will be yt P total equals to xt total, that is the mole fraction of toluene in liquid, times x P of toluene. So this we need to calculate yb, and we, as we know, that is the binary composition. So ya plus yb, or yb plus y total equals to 1. Similarly xb plus xt equals to 1. So from here we can write yb p total equals to xb pb, and y toluene we can write as 1 minus yb times P total equals to x, that is 1 minus xb times particular toluene, and these are two equations. So dividing two equations we will get yb upon 1 minus yb times total pressure will get cancelled, equals to xb upon 1 minus xb times 92 divided by that is 35. So xb is already given as 0.2, so putting these values we can get yb as 0.396. So this was a simple question. Using only the Raoult's law we can solve this question. Now in next question, the match the column is given, and on the group 1 dimensionless numbers are given, and on the other side group 2 their physical meaning or their definitions are their significant, the physical significance are given. So this question is basically this question. So here you should know the formula, you should know the physical meanings of different dimensional numbers. So Biot number is nothing but it is similar to Nusselt number, but the Nusselt number is for the convective heat transfer in liquid is to the conductive heat transfer in liquid, and whereas we denote the Biot number for the convective heat transfer or to the thermal resistance in a solid is to the boundary layer thermal resistance in liquid. They are moreover similar, only the thing is in Biot number we consider solid, and in Nusselt number we consider liquid. In the liquid, that is the convective heat transfer of liquid is to the conductive heat transfer of liquid. And here in Biot number we consider convective heat transfer in solid is to the conductive heat transfer in liquid. So clearly this Biot number denotes option 2, and this Kibit number we always know it is denoted as a mu by rho dAB, that is nothing but momentum diffusivity is to mass diffusivity ratio, and the Grashof number is denoted as the buoyancy force upon the viscous force. So this is basically one should remember this dimensionless number and their physical significance. So the correct option for this will be P goes to second and Q goes to third, that will be the D will be the correct option. Now in third question, for what value of Lewis number the wet bulb temperature and the adiabatic saturation temperature are nearly equal? Now what is actually the Lewis number? So first we will define Lewis number. So Lewis number is, in terms of definition, it is nothing but the ratio Prandtl number to Schmidt number, which is further it can be written as Cp mu by K by mu by rho dAB. Further, physically, if you understand what Lewis number is, so it is nothing but the energy transfer by heat flow divided by energy transfer by mass flow. So this is the physical meaning of Lewis number. Now wet bulb temperature and adiabatic saturation temperature consider where we have air and we have water. So for air and water system, at where the wet bulb temperature is the saturation temperature. So when air and water comes in contact at some temperature, there is a mass flow and heat flow. So at that conditions, the air will always try to get saturated with the water. So it will lose heat and it will give heat to water. So that heat is in terms of latent heat, and there's some water will get vaporized and it will transfer, it will become the part of air. So now this, so the latent heat which the water get is from air. So this is the latent heat where there is no temperature change of water, where the air get heat through mass flow, because there is, the vapor is traveling from water to air. So here the heat is traveling from water to air. So there is a mass flow, and this latent through this some heat is flowing, and at this also condition this heat is getting from, in terms of heat flow, water is taking heat from air and it is giving some heat, taking some heat from air, and some water, some part of the water is vaporizing and going to air, and then where the air is becoming saturated. Now here for this the adiabatic temperature means, adiabatic saturation temperature means this system is not taking any heat from the surrounding. That is the ideal condition, or that is the adiabatic saturation temperature. And the wet bulb temperature is the temperature where this air is saturated with water. Now no more water it can take, or no more vapor it can take from water, it is already saturated. So the temperature denoted is wet bulb temperature. So this is basically ideal conditions where the system is not taking heat from the surrounding, and this is the well temperature, the actual temperature. So the wet bulb temperature is always less than the adiabatic saturation temperature. Now here So we have denoted this Lewis number as the energy transferred by heat flow and energy transferred by mass flow. Now, whenever this adiabatic saturation temperature and wet bulb temperature are same, it means there is the heat flow, the energy transfer to heat flow and the energy transfer to mass flow are same. So it is basically nothing but the Prandtl number to the ratio of Prandtl number to skipping number is 1, which is defined as the Lewis number. So for the wet bulb temperature to be equal to the adiabatic saturation temperature, the condition should satisfy that the Lewis number should be equal to 1. That is nothing, the energy transfer by heat flow to the energy transfer by mass flow should be same. Now next question, solute C is extracted in batch process from its homogeneous solution A and C. Using solvent B, the combined composition of feed and extracting solvent is shown. So, and point M denotes the mixture, and this is the tile line where this point denotes the extract part, and this part is the refined part. This part, and this C is the solute already given. B is the solvent and A is the carrier which is carrying C, from which C should be separated. Now they are asking the what is the selectivity of C. So first we need to find what is the composition of extract phase, what is the composition of raffinate phase. So using this ternary diagram, as we know, we can find the composition of E. That is, in extract phase we are denoting XC, XB and XA. So clearly XC will be equals to the concentration of solute, which is 2, 3. This is 0.3. This fraction denotes, this line denotes the fraction. So this is 0.3 fraction. XB, that is solute, this point B, so it is approximately this B is 1, 2, 3, 4, 5, 6, 7, 8, 9. This is approximately, the XB is 0.6. This, sorry, XB. This XB denotes 1, 2, 3, 4, 5, 6. So this is XB is as 0.6, and clearly XA is, we can see it is as 0.1. So total should be 1, that we can add 0.3 plus 0.6, 0.1. So this is the composition in extract phase. Similarly, we can find the composition of various components in raffinate phase from this ternary diagram. So we are denoting XC, XB and XA in raffinate phase. So XC will be 0.2, this is 0.2, and XB is 1, 2, 3, 4, 5, 6, 7, 8 and 9. That is, XB is XA is 0.7, and this XB is again 0.1. XA is 0.7 and XB is 0.1. So we this composition we know in raffinate phase. Now what is the selectivity of C? So selectivity of C is defined as mass fraction of C upon mass fraction of A. This is extract phase, divided by mass fraction of C upon mass fraction of A in raffinate phase. So from this we know the mass fraction of C and mass fraction of this. So mass fraction of C in extract phase is 0.3 divided by mass fraction of A is 0.1. Here your mass fraction is of C is 0.2 upon 0.7. So if we calculate this is 10.5.
So in this question, at 30 degrees Celsius, the amount of acetone adsorbed at partial pressure of 10 and 100 mm Hg are given, and using Langmuir isotherm, describe the adsorption of acetone. What is the amount of acetone adsorbed at the given partial pressure? So here, this is basically a simple question that we need to know what is Langmuir isotherm. So we have X by M equals to Kpa divided by 1 plus K equilibrium Pa. This is also K equilibrium. So this is the governing equation that corresponds to the Langmuir isotherm, where X is the amount of acetone adsorbed per unit mass of adsorbent, K is the K equilibrium, and P is the partial pressure of acetone getting adsorbed. So here we can generate two equations. So we know in first case when the partial pressure of acetone is 10 kg, how much acetone is adsorbed. So we can write as 0.1 by M equals to K equilibrium 10 divided by 1 plus 10 kPa. So kPa that is K into K equilibrium. So similarly we can generate second equation as 0.4 by M equals to K equilibrium into 100 divided by 1 plus K into 100. So solving these equations, we can get the amount of adsorbent required is 0.6 kg and the equilibrium constant will be 0.02. So now using this we can go for the third case when the partial pressure of adsorbed acetone is 50 mm of Hg. So here we have X by 0.6 equals to K equilibrium that we have calculated into 50 divided by 1 plus 50 into 0.02. So from here we can calculate X, that will come out around 0.3 kg. So this much amount of acetone will be adsorbed per unit mass of adsorbent. So the option C will be correct.
Now next question, consider the following two cases of a binary mixture of gases A and B under steady state condition. In case 1, the diffusion of A occurs through non-diffusing B. In case 2, equimolar counter diffusion of A and B occurs. In both cases, the total pressure is 100 kilopascal and the partial pressure of A at 2 points separated by a distance of 10 mm are 10 kilopascal and 5 kilopascal. So assuming that the fixed flow diffusion is applicable, what is the ratio of molar flux of A in case 1 is to 2? So we have two cases. One is case 1 and another is case 2. Case 1 we are considering for equimolar. Case 2 is case 1 is diffusion of A occurs through non-diffusing B, means stagnant, where B is stagnant. And in case 2, equimolar counter diffusion is taking place. So here we can directly use the flux formula as J equals to minus DAB upon delta ZRT ln PB2 upon PB1. So DAB, and that is the total pressure. This is the equation used for stagnant fluids, and in case 2 for the equimolar counter diffusion we have the flux equals to minus DAB upon delta ZRT PAI minus PA2, where this is the pressure gradient. So using this relation Z, this is the case 1 and this is the case 2. Everything is same, only the term this is different here and this is different here. So dividing Ja1 divided by Ja2, that will be nothing but dab get cancelled, delta z will get cancelled, rt will cancel that, and it will come as P total ln of Pb2 by Pb1 divided by P of PAI minus PA2, and the total pressure is given as 100. ln of this Pb2 can be written as P total, that is 100 minus Pa1, and this Pa1 is given as 10 but 100 minus 5 upon Pa minus 100 is 10 minus 5. So solving this we will get ratio as 1.08. So this is Pa1 minus Pa2, and this is also this delta z. So Pa1 minus Pa2, so when we apply Pa total, so this sign will get cancelled and the negative sign will be maximum here. So here minus dab this, and we are applying this, so it will get minus this equation, and it will give the ratio of molar flux of A in case 1 is to case 2 is 1.08. That will be the option. So that's all for GATE Chemical Engineering 2016 paper for mass transfer. For more such videos, stay tuned, and thank you.